What is up, YouTube, and welcome to another video. In this video we're going to be talking about Kubernetes StatefulSets. In order to understand a stateful set, you have to understand what state means. So in software, all software has some degree of state. In some applications it's not obvious because the state of the application does not really impact us. Those are usually called stateless applications. Other applications like databases, message queues, caches have a much higher degree of state because they rely on storage. In this video we're going to be taking a look at stateless applications, stateful applications, and then we're going to take a look at how Kubernetes helps us with stateful applications with the concepts of stateful set. And then finally we're going to end up with a real life example where we run a Redis cluster in a stateful set on Kubernetes. The code is down below so you can follow along. And without further ado, let's go. So what is state in software? So let's say we have an application. This could be an ASP.NET, a PHP application, some Apache web server. It doesn't really matter. We have our customer, Bob. Let's say, for example, this server hosts our company website. Now, Bob opens up the browser and types the address of the website in the browser. The browser will then hit our server. The server will load HTML files from disk and send it back to Bob's browser. So Bob will reach and see our website and Bob is happy. But what if this server dies? That is why in web applications we normally have a second web server, and we also have the same HTML files deployed to the second web server. Then we use this thing called a load balancer in between, and we could send 50% of traffic to the one server and 50% of traffic to the other server. That means if one of them dies, our application is still available. Now the HTML files on this server is some degree of state. Now we can see even if the load balancer is requesting files from different servers, it doesn't really impact Bob. Now, although our application here has a very low degree of state, meaning that the state doesn't really impact Bob, this here is a stateless application. So because our application is just serving basic HTML files, there is no state that ties Bob's browser to our server. That means our application is stateless. Now, I always encourage people to build stateless application because managing state is hard. Now let's take a look at a stateful scenario. So let's say Bob has to log into our website. So Bob types in a username and a password. Usually when a login happens on a website, we generally take the username and password. After we've authenticated, we create this thing called a session ID and a cookie that we store in the browser. When the authentication happens on a web server, the web server is what generates the session and stores it in memory or on disk. So now any subsequent request that comes into this web server, the web server can identify that the session belongs to Bob and can serve the HTML files to Bob. Now what happens when this server dies? Or what happens if the traffic comes to the other server and there is no session available here? Well, Bob will be logged out and Bob will have a bad day. Now that is because the state of our application is tied to a web server. That's because the login information is tied from the browser directly to the server where it stores it in memory. This is not a good architectural design. Now, it is always a better architectural practice to decouple the state from this web server process. So in this case, what we may do is deploy a data store. This could be a memcache, Redis, it could be a database, whatever technology you prefer to manage. And then what we would do is we would remove the session store from the process and we would save the session in the data store. Now the two servers can come and go as they please. Since we have now decoupled the state from the process, and each one of these web servers can now access the same state in the data store. So now we're back at the point where we have a stateless application, and this over here is called a stateful application. Now, stateful applications like Redis, Memcache, databases, NoSQL or SQL may use memory for fast access to data, but it usually persists the data somewhere on disk. To make things a little bit more complicated, some of these stateful applications like databases may use its own replication technology to replicate data among multiple instances to achieve high availability. Now let's take everything we know and let's try to imagine us deploying a SQL database onto a Kubernetes cluster. So you're probably wondering, why don't we just use a Kubernetes deployment to deploy our SQL database? Well, a lot of people don't understand the differences between a deployment and a stateful set. So to understand this, let's take a look at the deployment. So let's take a look at a Kubernetes deployment. So in Kubernetes, you have this thing called a node or a virtual machine that you want to run some workloads on. So in a deployment, what we do is we normally create a pod. Now a pod, as you can see, has a random name and a random hash behind the pod name. And let's say we're deploying a SQL instance to this pod. We'll have a SQL container running in the pod. Now by default, SQL is not aware that it's running inside of a container. Basically, it's just going to write to the file system the way any other database process would. So it writes to the file system, and what happens is the container has a virtual file system attached to it. So that means any data that's written inside this file system is lost when that container is destroyed. Now with containers, we normally solve this problem by mounting the files from the host into the container. This is called a Docker volume. So if you do Docker run and you put the -v flag, you can mount a host path into the container path. So if we take a look at this in Kubernetes, we can actually mount files from the node into the container. And this in Kubernetes is called a persisted volume of type host path. Now Kubernetes has many different types of persisted volumes. I'm not going to cover all the different types of persisted volumes, as this is a stateful set video, but it's important to understand basics of persisted volumes and how they play a role in stateful workloads. So in this example here, we're using a host path to simulate a Docker volume. So what we're doing is now SQL is still accessing the files on the file system, but it's actually accessing the files on the host because the host is being mounted into the container file system. So this is 100 times better than our previous solution because now our data is persisted on the node, meaning if the container dies and gets recreated, the data still persists. And this might be okay for some small businesses that have a one node Kubernetes cluster and maybe they're running non-business critical workloads, but it's not good enough for business critical systems. If a machine gets recreated, the data is lost. If the machine's host operating system file disk gets full, the operating system is going to become unstable. Also, if the pod gets scheduled on another node, if you're running more than one node in the cluster, then the data is not going to be on that server. So you're going to have, again, data loss. Now, a much better improvement would be to take a look at other types of persistent volumes. As I mentioned before, there are multiple different types of persistent volumes. You have host path. You also have different types of persistent volumes that you can either attach to a single node like an SSD drive, or you can attach a network share like an NFS file storage. Every cloud provider also has their own set of persistent volumes, like Azure has Azure Disk, Amazon has Elastic Block Storage, and then you find open source types persistent volumes like Ceph and Storage OS. So in this example, I'm going to show you, let's just bring our own storage here, like an NFS network share. And what we do is we then use a different persistent volumes rather than host path, and now we can mount the files onto that share. So what we've done here is we've enhanced the persistent volumes by now, instead of coupling ourselves to the container, we've moved on to the host path, and instead of coupling ourselves to the node, we've advanced into an external type persistent volume. So now we no longer rely on the container or the host. So now we are in a much better place. But you're still probably wondering, what is wrong with a deployment? What is wrong with using a deployment here and multiple pods to store data? But there are still some fundamental problems with a Kubernetes deployment in this solution. So what are the problems? Well, if we take a look at this, the first problem is, what if we scaled up to 2 pods? So what if we created another pod XYZ? Now, the first thing that's going to happen is when Kubernetes scales a deployment, the pods are going to use the same persisted volume. That is because by default, pods as part of a deployment share the same persisted volumes across the cluster. So this is a problem for SQL, because what's going to happen is we're going to have 2 instances of SQL and they're going to write to the same storage. And what will end up happening is pod A will write to the same storage as pod B, which will result in a data corruption. The second problem here is that from a network point of view, pod ABC and pod XYZ don't have a reliable way of calling one another over the network. That is because by default, pods in Kubernetes don't get their own DNS names, and usually you use what's called a service to expose pods to other applications in the cluster. So that means SQL in this case is going to have a difficult time trying to set up a cluster and replication. So pod ABC and pod XYZ is not going to be able to make network calls to each other to form a master-slave replication. So by default, the only way to get traffic between pods is to create this thing called a service. Now this is okay if you have a client that wants to read the data in SQL, and because a service is load balanced between pods, but it doesn't help us if pod ABC needs to make a network call to pod XYZ. The other problem here is that if we take a look at the pod names, pods get a random hash assigned to the end of the pod name. So the pods don't really have a network identity, they don't have a DNS name, and every time a pod gets destroyed and recreated, it gets a new randomized name. And we all know from a data replication point of view, that is not going to be really good. If you have something like a Redis cluster where you have a node that gets created, joins a cluster, and then when it gets deleted and recreated, it has a different name, it's going to be hard for all the different instances to find each other in a cluster. So pods and stateful workloads need some form of network identity that's persisted among restarts. Now the final problem that I want to show you is if we scale up. So let's say we scale up to 5. What a deployment will do in Kubernetes, it will just randomly issue 3 more pods here. So this is because in Kubernetes, deployments just randomly scale up the number of instances, and also when we scale down, it will randomly terminate certain instances. And this is bad for something like a Redis cluster where you might have like a very delicate need for scaling. So you might want to create 1 pod at a time so that they can join the cluster and form part of the replication. The same thing goes for scaling down. So if we scale this solution down to 1 pod, what will happen is Kubernetes will just terminate them in random order and probably terminate them all at the same time. And if you try to scale a Redis cluster down to 1 at the same time, you're going to have a big outage. So just to recap, you can see firstly, pods in a deployment share the same persisted volume. Secondly, pods have a random hash character at the end of the name, so they don't have persisted identity. They also don't have their own DNS name, so they can't be individually addressable. And deployment scaling doesn't really help stateful workloads. Now, if we updated our deployment to be a stateful set of, let's say, 3 replicas, let's take a look at what improvements Kubernetes have made to allow us to deploy stateful workloads. So firstly, if we say we want 3 replicas, the stateful set will not issue 3 pods at once. Instead, it will create our pods one by one in a very delicate fashion. So here we will get a pod, and the pod will also get its own DNS name. So it'll start with the name of the pod and then the ordinal, which will start at 0. So every time we scale up, the ordinal number will increase. But the cool thing here is that if pod 0 gets destroyed and recreated, it will be recreated with the same DNS name, so that whoever wants to call it as part of a cluster will be able to address pod 0 again from a network point of view, even though the IP address might change. You can also see now that the pod name doesn't have a random hash. It has an ordinal number that starts from 0. And then the other thing we'll notice here is that every pod as part of a stateful set gets its own persisted volume. And this is one of the fundamental differences between a stateful set and a deployment. Deployments share persisted volumes. Stateful sets have their own persisted volumes between pods. In Kubernetes, Kubernetes, we can use the dynamic storage provisioner to dynamically provision persisted volumes when we scale up. So now we can see, since we asked Kubernetes for 3 replicas, the next thing it's going to do is it's going to create the second pod. And you can see the ordinal number over here has increased to 1. And what happens is Kubernetes will then dynamically provision that storage. So now we have 2 pods and they're both individually addressable. So if we were running a Redis cluster here, pod 0 and pod 1 could be the master node and form a cluster and join each other as part of the scaling process. So it's also good to notice here that the stateful set basically creates pods one at a time and makes sure that each pod is completely ready. It has its persisted volume, it has its DNS record available, and its network identity is persisted before it creates the next pod. So if we had another node, the same thing would happen there. So the third replica might start on another node and it will get its own DNS record, its own network identity, and the ordinal will go up to 2 and it'll get its own persisted volume storage as well. So you can see the scaling process and the deployment process of a scale set is a lot more delicate than a deployment. And the other thing I wanted to show you guys as well is a stateful set allows you to retain these persisted volumes when you want to scale down. So let's say we scale back down to 1 pod. So what will happen here, instead of like a deployment just terminating all the pods, the stateful set will basically start at the highest number and then terminate them gracefully. So we can see here our pod 02 has been terminated, but the storage has still been retained. So it allows us to keep the storage. And then the next thing that Kubernetes will do is it will then take the next pod in the list and then scale that one down, also retaining its storage. So you can see there's a delicate scale down process. So Kubernetes will take the highest number, terminate that pod, wait for that termination to be done, and then move to the lowest number in order. Now the same thing applies then when we scale back up. Kubernetes, as part of a scale set, will delicately scale one by one. So it'll bring that pod back. And notice that the pod 01 has the same DNS record, the same name. Even though the IP address might be different, it has the same DNS name. So its identity as well as its network identity has been persisted, as well as the storage. So it's going to be mounting the same persisted volume in again. And then when we scale up, the same thing is going to happen here with the last pod in the list. So you can see that it's a lot more delicate in terms of its scaling up and scaling down process, with trying to persist the data, persist the pod name, and persist its network identity. So one thing I want to make clear, and really clear, do not look at Kubernetes as a solution to make your application stateful. Well, what do I mean by that? As I mentioned earlier, data stores like Redis, Cassandra, MongoDB, Postgres, MySQL have clustering features. If you're planning to build a Cassandra, a MongoDB, a Postgres, a MySQL, or Redis cluster, you need to know what you're doing. Kubernetes StatefulSets is not going to help solve the clustering components for you, and you need to know how that data store will behave if the storage is moved, detached, or distributed. By understanding how the clustering in that application works, you can apply what you've learned about persisted volumes and stateful sets and come up with a great solution. So Kubernetes can totally work for stateful workloads if you know what you're doing. The other thing I want to mention is that you need to choose the right persisted volume for the right job. If you need high-speed read and write storage, you're going to have trouble having a network share, and you might benefit more from using something like an SSD storage. So make sure you educate yourself and read up about the different persisted volumes available. And the final thing I want to say is that if you're running in the cloud, there is a high chance that your cloud provider will already have a storage offering available for you. So if you're running in the cloud, they might already have a Postgres database as a service or a Redis database as a service. This may cost a few dollars per month or even a couple of $100 per month, but it might be totally worth it, as it'll take the burden away from your engineering team so that they can focus on what's important and not get stuck with data replication and high availability. So let's take a look at a real world Redis example running Redis in a stateful set. Right, so let's take a look at a real life example of a stateful set running Redis on Kubernetes. So for those of you who are not familiar with my channel, everything I do is on GitHub. So I have the Docker Development YouTube series, I have a Kubernetes folder. Inside here, I have a stateful set folder with statefulset.yaml, and as well as notes and an example application. So in my notes file, I have all the commands listed here that we're going to run now. So if you want to follow along, all the commands are recorded. So the first thing we're going to do is we're going to say kubectl create create NS. That's going to create a namespace which is going to hold all the resources that we're about to deploy. The next thing we're going to do is check the storage class. Now the storage class is basically all the provisioners for storage that runs within Kubernetes. So if you're running Kubernetes on Docker for Windows, or you're running Kind or Shipyard or K3s, or you're running in the cloud, there will be a storage provisioner for host path type volume. So you can see here I'm running Docker for Windows. I say kubectl get storage class, and I have a provisioner for host path. The name is what we want to record, which is called host path, and we'll take a look at that in a second. So what I'm going to do is deploy a stateful set, which is going to showcase everything I showed you guys and spoke about earlier, as well as create an example app that is going to be talking to our Redis cluster. Let's take a look at that. So if I say kubectl in the example namespace and I say apply, I can apply my stateful set file. Now before we do that, let's take a look at what that file looks like. So on the left hand side here in the Kubernetes folder, in the StatefulSets folder, we have statefulset.yaml. Now you'll probably notice that a stateful set YAML structure is almost identical to a deployment. The only subtle difference is that we need a service name. So we need to define a service that's going to be exposing our pods. Then what we have is we have number of replicas, and we're running an image. So a normal pod spec that you can see here. So we're running an image of Redis 5.0. We're exposing a port. We have an entry point to start up our Redis. We have an environment variable to get the pod IP address. And then here's the crucial part. For our Redis to persist data, we have a mount path to a folder called /data. That means Redis will write its files into a file system on a folder on /data. But the way it will persist the data is through a volume claim. So what we have here is a volume claim template. So this is going to use the dynamic provisioner of Kubernetes to provision a volume for each one of the pods that get created. So here we're going to create a volume called data, and it's going to have this access mode, which is read write, and then it's going to use the storage class name that I mentioned earlier. This is the name you want to grab when you do kubectl get storage class. Our name was called host path. Yours might be something different depending on your Docker installation, depending on your Kubernetes cluster installation and where you're running. And we're going to go and request 50 megabytes of storage inside of this volume. The other bit that we have down here is just a simple service. This is a service that is required for the stateful set to be exposed. So we can expose our Redis instances to other applications. So we're exposing this port and we're exposing this port. Now the next bit is going to happen pretty quickly. So what I'm going to do is I'm going to say kubectl apply in the example namespace. I'm going to apply this YAML. Then what we're going to do is we're going to quickly say kubectl get pods, and we're going to see that each pod gets created one by one. So a stateful set allows each pod to become ready before creating the next pod. So if I do kubectl apply and then I do kubectl get pods, you can see we have one creating. If I run it again, we can see we have two. And as I'm running this, we can see it's increasing, right? We have 3, we have 4, and eventually we're going to have 6. Now, if I run kubectl get pv, you can see the same thing is happening for volumes. Kubernetes will create the pod, it'll create the volume, it'll assign that volume to that pod, and then move on to the next pod. So that is the beauty about stateful sets. It helps us to scale much more delicately than a deployment. So now we can see we have 6 instances of Redis running. The next bit is we're going to create an example app, but before we do that, we have to enable the Redis cluster. So I have these 3 commands. So the first thing we're going to do is we're going to grab the IPs of the pod. So we're going to grab that into an environment variable, because by default, the Redis cluster has not been created. We only have 6 Redis nodes. We have to go and set up the cluster. So then the next command, what we're going to run is we're going to say kubectl exec into one of the Redis pods, and we're going to run this cluster create command. That's going to set up our Redis cluster. We type yes, and it's going to send the cluster meet messages. All the nodes are going to join the cluster, and we're all good to go. And to confirm that, I have another command here, and basically that command will also run an SSH command on the first node, and it's going to say Redis CLI cluster info. This is going to grab the state of the cluster. We can see the cluster is okay, and there are 6 nodes part of the cluster. Now in this example, the first 3 nodes are going to be master nodes, and the last 3 nodes are going to be slave nodes. If you want more information on this Redis cluster, feel free to check out this Rancher blog. This is where I got the information from. This is just an example that I needed to showcase how persistent volumes, stateful sets, and clustering works. Now the next bit I'm going to deploy is this example application. This example application is pretty much just a counter. So we're going to hit a website, and every time we hit the website, the counter is going to increment by 1, and it's going to store that increment in the database. So what we're going to do is we say kubectl apply in the example namespace. We're going to deploy this example app. Then if I head over to the browser, we can see our application is up, and this is the counter. So every time I refresh this, the counter goes up. So we can see I've hit it 10 times. So now the counter is stored in the database, so we can go and test our capability to persist data. And now I want to show you guys what this stateful set is capable of doing. So if we say kubectl get pods, we have 6 pods. Now what I'm going to do is I'm just going to run a command to say delete pods, and I'm just going to randomly delete a few pods. So I'll delete the first one and I'll delete that one there. Now that's going to go ahead and delete those pods. They're going to terminate gracefully one by one from the highest number to the lowest number. But notice when I go to my browser and I refresh this, I've not lost any data. We're now on 11. So I can go ahead and go all the way up to 20. We have no data loss because we have a cluster set up. The data is persisted on a persisted volume, and there's no state in the process itself. The process will be killed, recreated by Kubernetes. So if we do kubectl get pods again, we see we have our 6 nodes up and running with no data loss. Now, what if I scale this cluster down? So let's take a look what happens if I say kubectl in the example namespace. I say scale StatefulSets Redis cluster, and I say I want to go down from 6 to 4 replicas. So if I do that and I do get pods, we can see it's terminating the pods one by one, and then eventually now we'll only have 4 pods running. And if I go to my browser, I have still no data loss, right? So Redis is taking care of the replication, and it's storing it on multiple pods, and it's synchronizing it with those Redis instances and storing it in persistent volume. The other thing you want to notice as well is the persistent volumes are all retained. They're all still there. So the data is still there. I still have 6 persistent volumes, even though I only have 4 processes. That means when I go and I scale back up to 6, Kubernetes will create one by one again containers and mount them to the same volumes, not new volumes, so there's no data loss. To go back to our browser, we can still keep going, and I can go all the way up to 40. So this shows you how persistent volumes work in conjunction with stateful sets and clustering. Now I want to show you guys a little bit more severe example. So what if we scale this down to 1? So what I'm going to do now is I'm going to say scale replicas down to 1. So let's say we had a bigger outage and almost all the pods were terminated, and now we can see we only have 1 pod running. And if I do get persistent volume, we can see we still have all the data retained. So the persistent volume is doing its job of keeping the data in the volume. The stateful set is doing its job by keeping processes mounted to the right persistent volumes. But now let's go and take a look at our application. So if I refresh this counter now, look what happens. Now we've lost connectivity with our Redis data store. So what has happened under the hood? Well, let's go and run this command to get the status of our Redis cluster. So I'm going to say kubectl exec on the first node of that Redis instance. I'm going to say cluster info, and now we have a cluster fail. We also have cluster sizes 6 nodes, but now the cluster is down. So this goes to show that when you're storing state on Kubernetes, it's not all about persistent volumes, stateful sets. Kubernetes doesn't do the job of making sure our cluster on our Redis is healthy. So now we pretty much have a Redis outage, and this is where your engineering team is going to have the knowledge of how to get that cluster repaired and get it back up and running. So it's not always just a matter of saying, okay, let's scale back up to 6. If I do that and I do kubectl get pods, we can see that Kubernetes will go and recreate them gracefully and bind them to the same storage. So technically speaking, we shouldn't have an outage, right? But still, if I refresh this, we have a cluster outage. Cluster is down. So even though we have all our instances running, it takes extra engineering overhead to make sure that you understand the clustering of Redis and how to repair that cluster when it goes down. So I hope this video helped explain and clear up and demystify how stateless and stateful workloads run on Kubernetes. And this will help you make more smarter, informed decisions around how to run stateful workloads on on Kubernetes. So remember to check out the links down below for more videos on my Kubernetes development guide, as well as other videos in the DevOps space. And let me know down below in the comments what sort of videos you'd like me to cover in the future and how you manage state on Kubernetes. And remember to like and subscribe, and until next time, peace.